All right, welcome. Today, we are jumping headfirst into the world of organic nitrogen compounds. Now, these molecules, they're kind of the unsung heroes of biochemistry. They really are the foundation of life as we know it. So let's get right into the chemistry that makes everything, from your muscles to your DNA, possible.
And that really brings us to the big question for today, doesn't it? What is it about nitrogen that makes it so critical, so indispensable? Why do we call it the backbone of biology? Well, the answer is all about its unique chemical personality, which we're going to explore through a really fascinating family of compounds.
So, here's our game plan. We're going to start by meeting the family. That's amines, amides, and amino acids. Then we'll dig into the power of amines and solve this little puzzle about their basicity. After that, we'll see how they stack up against their neutral cousin, the amide, before putting it all together to see how amino acids literally build life itself. And we'll wrap up by checking what we've learned. Right, let's get into it. Our three main players for today are amines, amines, and amino acids. You can see right away they all have that nitrogen atom, but the stuff they're attached to, well, that makes all the difference, giving them totally different shapes and, as you'll see, dramatically different personalities.
This table here really lays it all out. So you've got the amine, which is the simplest of the bunch, just a basic nitrogen atom. But then look at the amide. See how that nitrogen is right next to a carbonyl group? You know, that carbon double bonded to an oxygen? That one little change completely flips its personality. And finally, you have the amino acid, which is this cool hybrid molecule that has both an amine group and an acidic group. So let's zoom in on our first family member, the amine. If an amine had one defining trait, one thing you'd remember about it, it would be its basicity. They are pretty much the quintessential weak bases you run into in organic chemistry.
Okay, so why are they basic? It all comes down to that lone pair of electrons sitting on the nitrogen atom. See, that pair isn't tied up in any bonds, so it's just available. It's sitting there, ready to reach out and grab a proton, an H+ ion, from its surroundings. And that action, accepting a proton, is the very definition of what a base does.
Now here's where it gets really interesting. This chart shows us that not all amines are created equal, not even close. You've got ethylamine, which is a stronger base than plain old ammonia. But then you attach that same nitrogen to a benzene ring to make phenylamine, and its basicity just tanks. I mean, it plummets. Why? Why the huge difference? That's the puzzle we need to solve.
All right, time to solve this basicity puzzle. It turns out, an amine's actual strength when it's in water isn't about just one simple thing. Nope, it's this delicate, fascinating dance between three competing effects. Let's break this down. First, you've got something called the inductive effect. Basically, alkyl groups, carbon chains, are generous. They push electron density towards the nitrogen, which makes that lone pair even more eager to grab a proton. Makes sense, right? More push, stronger base. But wait. Once it grabs that proton, it becomes positively charged, and it needs to be stabilized by water molecules. That's the solvation effect. More stability, stronger base. But there's a catch. Steric hindrance. If those alkyl groups get too big and bulky, they physically get in the way, blocking water from coming in to help. That makes the whole thing less stable, and you guessed it, a weaker base. So the most important thing to remember is this. An amine's basicity in water is a constant tug of war. It's this push from the alkyl groups, the stabilizing pull from water, and the physical blocking from bulky groups all happening at once. The final strength of the base all depends on which of these forces wins out in that specific molecule. Okay, so with that complex picture in mind, let's move on to our next character. Meet the amide, which I always think of as the neutral cousin. After all that talk about amines being bases, amides are, well, shockingly neutral. And this slide tells you exactly why. Remember that free, available lone pair on the amine? Well, in an amide, that neighboring carbonyl group is so electron-hungry, it basically pulls the nitrogen's lone pair over for a visit. The electrons aren't just sitting on the nitrogen anymore. They're spread out or delocalized across the nitrogen, the carbon, and the oxygen. And because that lone pair is no longer available, the amide can't accept a proton. It's been neutralized. This quote really just says it all, doesn't it? That delocalization, that spreading out of the lone pair into the carbonyl group, is the single most important feature of an amide. It's what makes it neutral, and as we're about to see, that neutrality is actually a superpower. And now we get to the absolute star of the show, the amino acid. Seriously, this molecule is a work of art. It's a masterpiece of chemical design that combines the personalities of both amines and acids to become the fundamental building block of, well, us. So what exactly is an amino acid?
At its core, it's this amazing molecule that has two completely different personalities living under one roof. You've got a basic amine group on one side and an acidic carboxylic acid group on the other. And it's this incredible dual nature that gives it all of its amazing abilities.
So, think about it. What happens when you put an acid and a base on the very same molecule? They react with each other. The acidic end donates its proton over to the basic end. This creates something called a zwitterion, a molecule that has a positive charge on one end and a negative charge on the other, but is perfectly neutral overall.
This whole zwitterion thing explains so much about how amino acids behave. Because they're basically little internal salts, they have super strong attractions to each other. That's why they have such high melting points. It's also why they dissolve so well in water. And because they have both an acidic bit and a basic bit, they can act as buffers. They can soak up extra acid or base to resist changes in pH, which is absolutely vital for keeping our bodies stable.
So how do we get from these individual amino acids to a giant protein? It happens when the acid group of one amino acid reacts with the amine group of another. This reaction forms an incredibly strong and stable amide link, which in biology we call a peptide bond. And this is why the amide's neutrality is so important. This stable, unreactive backbone is what allows a protein chain to exist and fold into all sorts of crazy complex shapes without falling apart. And then this process just repeats over and over, linking hundreds of thousands of amino acids together to build the proteins that run the world.
Okay, wow, we have covered a lot of ground. So let's put all this knowledge to the test. We're going to do a quick check to see how these ideas play out in a real-world example.
All right, take a look at these three molecules. In the middle, you have phenylalanine. On either side, you have variations with different groups attached. Now, based on everything we've just talked about, electron-donating groups, electron-withdrawing groups, can you rank these from the strongest base to the weakest?
And here's the answer. 4-methylphenylamine is the strongest base. Why? Because that methyl group is electron-donating. It helps push density towards the nitrogen, making it more basic. On the other end, the chloro group is electron-withdrawing. It pulls density away, making that lone pair less available and making it the weakest base of the three. Phenylamine, with no help and no hindrance, sits right in the middle. Makes sense, right? That ability to tweak basicity is just one tiny example of how small changes have huge effects. And that brings us to one of the most beautiful and elegant facts in all of biology. Out of all the amino acids that could possibly exist, life has decided to build almost everything out of just 20 common types. Just 20. The entire mind-boggling diversity of proteins in your body is built from a simple set of just 20 molecular Lego bricks.
And that leaves us with one final massive question. We've seen that a protein is really just a long chain of stable, neutral amide links. So how on earth does that simple-looking chain manage to fold itself into the incredibly intricate three-dimensional machines that perform all the complex tasks of life? Figuring that out is the next giant leap. But that, my friends, is a story for another explainer. Thanks for joining me.